but give the approximate location of a local maximum of this function. So I guess you could have done some of it by hand. You could have taken the first derivative, set it equal to 0, solved for critical numbers, and then you would know the x locations that are possible maxes and mins. You could test around those critical numbers to figure out which one is actually a max. But then the y value is such a weird decimal. Plugging in this decimal and evaluating the y value is where you should get stuck at the end. So, but with the calculator, and like several of these other questions, I think this was actually a released question, by the way, and I'm pretty sure it was in the calculator section. There wasn't like more information to it. So the easiest way to do this one, if it was phrased the same way on the AP exam, is just graph it. Say, well, if you're going to graph it, you better graph it correctly, though. And then, can you see where the max is? Okay. And the x value is something negative, so that throws out choice A, C, and E real quick. Yes? Choice B and D both have the same x value. So if you hit tangent or trace 0.2457 enter, it will jump to oh, why would I do that? Never mind. I said that backwards. We want the negative one. This is the min. Okay, trace negative 1.357 enter, and it will take you exactly to that point. When x is this value, y is, well, how come it's none of these? It should be choice C. But
well, it says give the approximate, so you can choose closest one, so A.
Yes, you would have to, since it says approximate, that's why it doesn't look exactly the same. Sorry, it should be A. C is very close too, but A is a better answer. So based on the decimals of that one, it would need to be done with the calculator. But if you have a calculator, then definitely the best use of your time is just to graph it and look for the max. Just because you could do the calculus to find the max, that is a slower process.